Hello Internet, my name is Quinn and this is Blondihacks. This is the final video in the D-bit grinder refurbishment. We got some loose ends to tie up, and I mean that literally. There's some stuff that's loose and shouldn't be, so let's go. First problem we're going to tackle is the runout in the workhead. You may recall previously we established that there was about 1,000th of runout in this guy, so that's a high quality end mill there, and you can see that we're getting about 1,000th, and that seems high for this machine and for a good quality collet. Now, we established previously in this series, way back in part 4, that the runout is not coming from the workhead itself. If I indicate on the taper where the collet sits, it's basically 0 runout. Now, I should be doing this with a tenths indicator, not a half-thou indicator, but it's what I have, and tenths indicators are very expensive. Sidebar. I actually tried to buy a tenths indicator to finish this job on eBay. I finally found one for a reasonable price, ordered it, was very excited. It arrived completely broken, and it was not a tenths indicator. The seller had lied on both counts. So yeah, buyer beware on eBay. Anyway, as I was saying, we established that the runout is not coming from the workhead, so that means that there's something wrong with how the collets are sitting in the workhead. Before we go further, a little bit of context. I did try marking where the runout was in the rotation and reseating the collet different times to see if it was coming from somewhere consistent. That would tell us perhaps the nature of the problem. I experimented with 1/1000 shims to see if I could remove the runout by positioning shims, and what I found was that it was not consistent. The runout was not repeatable, so that tells me it's something about how the collets are seating. To test that hypothesis, I cleaned everything thoroughly with lint-free wipes, and I got out our old friend Prussian Blue. This is kind of like Dicam, except that it doesn't dry. You can put it on very thin onto a surface and press it into a mating surface, and the dye will transfer and tell you how well those surfaces are mating together. And I clamped an end mill in there so that the conditions of that seating are exactly as I was measuring previously when the runout was apparent. And everything on the collet looks good. I don't see any major high spots or low spots. And then inside the workhead, again, everything looks quite good in there. There's a pretty even stipple pattern there where the surfaces are mating, so I don't see anything obviously wrong there. So the next thing I tried was just really thoroughly cleaning these collets, because I did find that there was quite a bit of grit in and around them, as you would expect from a grinding implement. And so after a very, very thorough cleaning of this particular collet, I tested it again, and now we're down to about 3 or 4 tenths of runout. So I think it was actually just that the collets are dirty, and so they weren't clamping consistently on the end mill, and they perhaps weren't compressing consistently inside the taper where they sit. Okay, but is that good enough? Well, for some perspective here, let's look at Hardinge collets, a very respected brand. They have 2 types of collets, their regular and their special accuracy. From their own website, their regular collets only guarantee 1/1000 of total indicated runout, and their special collets only guarantee between 2 and 5 tenths of runout, depending on the size of the collet, and this is only when mounted in their super precision spindle. The takeaway here is that collets are very precise, but they're not as precise as I think people tend to think they are. So to get 4 tenths in a Taiwanese copy of a decal collet mounted in a 25-year-old bushing, I think it's pretty darn good. The next problem I want to look at is the depth stop here on the workhead. This big knob is supposed to control the stopping point for the workhead when you swing it in and out, because that's the motion you use for grinding, and it doesn't seem to be working. It's not actually stopping anything. So I'm going to take the bottom off of here and have a look at what's going on. You can see there's an arm there that is supposed to ride on that stop. So with the stop cranked all the way in, you can see that it's not really stopping the workhead until it's much too late. Let me just pause here for a moment and say that you may be yelling at your TV right now that I'm chasing the wrong problem, and I do eventually figure it out, so bear with me. My first thought was that maybe that set screw was coming loose on the arm because there was a lot of leverage on it, so I put some Loctite on that guy and tighten it up real good. I did my best to align the arm such that the knob all the way in would put the workhead at the best position for the maximum range of motion that you would want in normal use. And this all seemed to be going well. I had a position that seemed to work well, and around this time is when I realized that none of this actually matters, because you can rotate the workhead independently of the bar, so that lever arm is actually the stopper for the bar, not the workhead. So it doesn't actually matter where that arm is relative to the position of the workhead, because you can always just loosen the workhead, rotate the bar by hand, and get a different position. So Eventually I did figure that out, as I say, and let's move on to the next problem. Now the next problem are these two locking handles here on the sides, which I mistakenly believed were supposed to lock the rotation of this bar in place. And they certainly did not seem to be doing that, so there was obviously something amiss there. And the handles seemed to be bottoming out without really doing much, so I took a longer fastener, the same thread, and screwed it in there. And that was still not working to lock the head, so there was something else going on. But this is the point where I realized that the left handle actually just locks the micrometer stop, so that one's actually working. So that's all fine and dandy. And when I had the handles out, I took a look in there and I saw the problem. The left handle has a brass plug at the bottom that is actually pressing on the bar, or in this case the micrometer assembly, and the right handle, which is supposed to be the lock for the bar, does not have a brass plug in there. And that's very typical for an assembly like this, to have a brass plug at the end to keep from galling up the important precision bar there. So what I needed to do was make a new brass plug because the existing one was missing. Maybe it got lost in disassembly, maybe it was never there, who knows. Now if only I knew someone who hoarded brass with the dream of someday swimming in it like Scrooge McDuck. Oh wait, that's me. So over to the lathe with an appropriately sized chunk. And we'll get one of my favorite brass tool bits in there. This is a simple 85-degree tool with a pretty sharp nose on it. This is one of the many reasons I think brass is a great choice for beginners. In addition to being very easy to machine, the tool bits are easy to grind because the ideal top rake is 0, and so that gives you one less angle that you have to grind on your tool bits. Very good thing when you're trying to learn how to grind tool bits. With that diameter turned down, we can square up our tool post with the parting blade and get ready to part this guy off to length. And actually before we do that, I should chamfer that end fairly generously so that it will slide in and out and not catch on any threads or anything that might be inside that hole. And now we can part it off. And when I'm partway through, I take a pause and I go in there with a file and just deburr the back side of that plug. And Yahtzee. Alright, our little plug looks good, and we just gotta clean up the back side of it there. The parting blade left a little nubbin, so I'll file that guy down. Many of my viewers have suggested beveling the front of the parting blade to prevent this little nubbin from being left behind, and thank you very much for that suggestion. I am aware of it, but it doesn't work with this parting blade because it's too thin. If you bevel the front of it, it causes deflection in the blade, causes binding, so it doesn't work with every parting tool, but I am aware of that trick. Alright, that looks like it's going to work, so we just slide that plug in there and snug that guy up. Moment of truth time. Hey, look at that, it works. I can tighten it, I can loosen it, and it locks that workhead in place just like it should. So that's good news. That's locked in there rock solid. The whole machine shakes when that thing is locked. That's a good sign. I wasn't actually sure how well this would work because that workhead is quite heavy and there's a lot of leverage. There's a lot of weight hanging quite far away from that bar. But this lock actually holds it very solid. So the next mystery is this locking handle right here. I couldn't actually figure out what it does. It locks and it unlocks, and I can tell that it's doing something, but it doesn't seem to affect any mechanism on the machine. Eventually I figured out it's supposed to be locking this indicator ring, and it's not doing that. So time to take this mechanism apart so I can figure out why, and back to our tools here that I made previously for these nuts, and we can pull this workhead off of there and try to figure out what's going on. So there's that locking handle, and the ring is doing nothing. Now this mechanism, the way this is supposed to work is this locking handle has an eccentric in it that's supposed to be pulling that screw head down and locking the ring in place. It's not doing that. So we can pull this guy apart. And in fact, when I rebuilt this workhead, I commented on how interesting this mechanism was, but I also commented on how difficult it was to adjust correctly. So here we are. So there you can see the eccentric, and that eccentric rides in the casting and causes that center shaft to go up and down relative to the casting, which then moves that assembly up and down that has the screw in it, and the head of the screw is supposed to lock that ring in place. So basically I just had to make repeated small adjustments, lock it in place with the jam nut, reinstall the entire assembly, test fit it, see if it worked, rinse, repeat many times. And these parts are all interrelated, so you kind of have to assemble them all at once. So there's no easy way to test as you go. So it was just a lot of trial and error to get that lock to work. But eventually I did get it. And then it was time to reassemble this workhead and put those nuts back on. And this was a little bit tricky because you got to get the tension on these nuts just right so that you get smooth rotation of the workhead, but with no end play in it. So that took, again, quite a bit of trial and error, but eventually I did get it. And now that works perfectly. So swing the handle one way and locks that ring, swing the handle downwards, and the ring is free to move. So we are back in business. Next order of business is the diamond dresser, which I kind of forgot about when I was doing the refurb of everything else. So I take this guy apart. Oh no, more of those little thrust bearings that I had so much trouble getting. And now it seems I need 2 more of them. Well, we'll see. Let's get this guy apart and refurbish it first. So the adjustable diamond pulls out the end of that tube. And well, actually it's 2 pieces. So the tube, there we go. The diamond comes out separately and it's got its own little threaded shaft there. You can see the diamond appears to be brazed into the end of that. This is a really cool part. This is another one of those differentially threaded parts. There's threads on the outside and the inside, different pitches, which gives you a finer adjustment than would be possible with one thread or the other. Cool mechanism. So this whole mess goes in the evaporust. And then about an hour later, quick rinse, and these parts are like new. This evaporust is great stuff. Hashtag not sponsored, but it really does work well. Now let's take a look at these bearings. These guys are actually in quite good shape, so I think I may just reuse them. And check out the finish on this bolt that mounts the whole assembly. Just amazing. That shoulder is better than anything I've ever seen, honestly. And this mechanism is really cool. There's little O-ring seals at both ends of this tube to keep the grinding grit out of it, which is no doubt why everything's in such good shape. This machine is just quality top to bottom. It really is well made. I'm using just a little bit of light assembly lube on things to make sure that we don't damage anything as we go. And here's another look at that diamond. It's in pretty bad shape, but I'm honestly not sure how you would replace it. I guess you'd have to replace the entire end of this thing. It seems to be brazed in there. I'm not sure if you have to order that part from Coolman or what is the deal there. But I probably won't end up using it much. I don't plan to run aluminum oxide wheels on this, which is where you would need the dresser. So back to reassembly. I'm going to oil up these bearings with some white oil, and as I said, they actually are in very good condition. They're not noisy, so I'm just going to reuse them because they're honestly not that critical. And the mounting bolt goes back in there. There's nothing really retaining all those bearings except the final assembly here. So into the main casting we go. Get that guy nice and tight, and the mechanism is designed such that you can tighten that bolt all the way, and then the thrust bearings get the correct amount of preload on them, which is pretty clever. And then the diamond dressing tool goes in the end, and it gets clamped down. And Bob's your uncle, we've got a diamond dresser. Okay, now on to the hub that mounts the grinding wheels. So I had this diamond cup wheel here temporarily mounted on there. This was an eBay purchase. And so we're going to disassemble this guy again using that tool that I made in the very first video in this series. And this guy's in good shape. It's mostly just rusty, so I think we can tidy that guy up with some evaporust. And this is really cool. It's got these adjustable balancing weights on the back, which are especially useful for aluminum oxide wheels, which do need quite a lot of balancing. That's a neat feature. Let's talk real quick about wheel balancing while this evaporust is doing its thing. I do intend to balance this wheel, but I need a wheel balancer, and they are weirdly expensive, but not that difficult to build, so I'm going to build one for a later time. But for now, since I'm not running aluminum oxide wheels, balancing is a little less critical, so I'll do kind of a rough balance with those weights just kind of evenly spaced, and it runs fine that way. So with everything clean and de-rusted, we've still got some crud on the front face there, and this turns out to be goo and old paper labels that have transferred off of aluminum oxide grinding wheels that were mounted, so the evaporust did not take that off. So a little bit of 320 grit emery paper and some Scotch-Brite did the trick there. And to prevent this guy from rusting again, I'm going to apply BoShield T9. There's a link to this down in the description. It's kind of my go-to rust preventer when you don't want to oil things, such as in a high grit environment like this. Next task is that janky plug that was on it. Yes, that thing's pretty terrible. So let's go ahead and replace that guy. A nice, shiny, and safe new plug is like $3 on Amazon, so there's really no reason not to do this. And it's a very quick job. We just gotta pull the old plug off of there. And here's our new plug, and these are pretty self-explanatory. You feed the wiring through. Now, they do have these screws on here and those clamping plates that are designed for loose wires. I don't want those because we have rings, so I just pulled the screws all the way off, removed those plates, put the rings on, tightened them back down, and reassemble the plug. And Bob's your uncle, we have a brand new electrical plug. Or maybe your uncle is Richard or Phil, I don't know. I'm sure your uncle is very nice. Or maybe he's one of those creepy weird uncles. You know, everybody's got one. Okay, let's get to dust collection. So I had this weird, crazy idea, first of all, to build a shroud like this that would kind of enclose the entire area around the grinding wheel and the workhead, and then a shop vac would plug in there, and it would mount with lock line using that pink lock line connector there. So I modeled all this in Fusion 360, and I thought, I bet I can 3D print this whole thing. I started off by 3D printing some basic half-inch lock line segments, and these guys, they worked okay. At this point, I did not have the official lock line pliers for assembly, and while I did get this guy to push together, they cracked right on the layer lines, which is always where 3D prints crack, and this is kind of a rookie move on my part of 3D printing because you always want to align your layers perpendicular to wherever the most force is going to be. So I gave up trying to print the lock line itself, and I just bought the real stuff on Amazon. It's actually very cheap, and I just 3D printed some lock line connectors, and I tried all of the ones that are on Thingiverse. None of them work very well. These models were actually the official models of the segments from Lockline, which you can get inside Fusion 360 using their parts for CAD system. I can't share those models because they are commercial and you have to pay for them if you're not a Fusion user, but just know that the official Lockline geometry prints extremely well. So then I tried to 3D print that entire shroud assembly, and this was going to be a 12-hour print, and 2 hours in it died. I have no idea why. This is part of why I have a love-hate relationship with 3D printing. Gave up on that idea, decided to do something simpler. So now I'm just 3D printing the shop vac mounting coupler with the lock line segment attached to it, and I'm going to make the shroud portion another way. So we pull this guy off of the bed, and that's looking good. You can see the support material under and inside the lock line connector, so that's a pretty straightforward thing to remove. Once that guy cleans up, now we can see if it actually works. And this guy was very, very tight in there. So I tried every trick I could to get it to push on there, and well, yeah, it split on the layer lines once again. So rather than adjusting my dimensions and printing that part again, which would take another couple of hours, I just took the segment I'd printed previously, which I knew worked very well, and I just filed it to match the profile, and I just epoxied it in place, and this worked very well. So here's our project so far, and that attaches nicely to the official lock line. And then there's a connector on the other end, which conveniently slides over the accessory post on the grinder. You can see that I also tried printing lock line at some smaller sizes, and that didn't work very well. And if you are going to 3D print your own lock line, make sure that they are compatible with the official lock line pliers, which mine were not. These pliers are kind of a must-have for assembling lock line. They're not very expensive, and they really do make it much easier. Now onto that shroud. So I looked in the junk bin, and I found this conveniently placed for film purposes piece of acrylic, and I feel like I can probably form this into that kind of 5-inch half circle that I need. So, oh yeah, that's the stuff. All right, with the protective coating removed, my plan was to just heat it over this aluminum slug and shape it into what we need. I was a little worried that these rolled edges would cause a problem, and yeah, spoiler alert, they did. Now, in fairness, my only experience with heat-forming acrylic was from a book holder that I made in shop class in 9th grade, and I literally have not done it since. So this didn't work very well. I got bubbles and other weird issues, but I thought I'd proceed and try to make it work. So then I went over to the drill press to cut the hole for the vacuum hose, and that went okay. It cracked a little, but it was okay. And then I thought, okay, now I just need to form my hose coupler to it, but the curve was such that there was no way to make it fit, and yeah, this whole idea just fell apart. So I gave up on the shroud at this point. Comes in women's and men's in lots of cool colors. Blondihacks.com/store. To mount the lock line on the grinder, I printed this clamp for the accessory post, and I guess I scaled it by 2x somehow in the software, and it came out completely the wrong size. Yep, 3D printing and me just don't get along. But I did find that that piece of lock line sample that I'd printed was a perfect fit over the top of the post, so I just used that. And a little test fit with the vacuum hose here. And the trick that I'm using here is that my shop vac has this accessory mode where you can plug in your tool, and when you start the tool, it turns on the shop vac and vice versa, which is a great feature. Let's do a little test to see if this is actually going to work. So I'm going to run the machine, and I've got some flour here that I'm going to sprinkle in the area where the grinding would happen. And you can see that it's getting some of it, but a lot of it is falling down on the machine there. So this suction is not high enough, I don't think, to really capture the amount of dust that I want. So we need to try something different. I think a concentrator on the end of the hose is going to be needed. So I'm trying the one that came with the shop vac, and it happens to fit in that ring that I made, so I give it a shot here. But yeah, you can see that the concentrator has too much leverage on the lock line, and the weight of the hose makes it such that I can't position it properly. So I decided to design and 3D print my own little nozzle. This is not a very elegant model, but it only took me about 5 minutes. Okay, let's get that guy off the build plate. Easy, easy. Perfect. Yeah, I never found that. I had to print it again. Now, it might be nice to combine this nozzle model with the other one that I made that attaches the hose, but again, that was going to take hours of extra 3D printing, so once again, I just epoxied them together, and a little test fit on our hose, and that seems to work very well. It doesn't look at all like an alien spaceship. All right, let's do another test on here. So we install this guy on the lock line, and that seems to work much better. The weight of the hose is still a minor issue, but it works a whole lot better. And the flour test, yeah, that's much better. So I think this is going to be sufficient. Okay, let's do an all-up test here of the system. So power up the grinder, bring in some tool steel here that I've got as a little sample. And yes, I know you're not supposed to grind tool steel with diamond, but it's good enough for Robin and Stefan. It's good enough for me. So we'll put a little chamfer on this guy. And our dust collection seems to be working. I mean, it's hard to tell with this kind of grinding grit because you can't really see it. But that chamfer sure turned out nice. And the stops all worked. And the levers and locks all worked. So I think we can finally call this D-bit grinder refurbished. I'm really happy with where we ended up, and it's now, I think, ready for use. Still got to build a balancer and, you know, some other miscellaneous projects around this machine, but I'm very happy with the result. Thank you very much for watching. Please do consider supporting me on Patreon, and we'll see you next time.